and again, another thing that impacts on transmission time is the data rate. If you increase the data rate, the transmission time goes down. And again, as a percentage of the total time sending and waiting, the transmission of the real data goes down. So for high data rates, we'll get similar to this, because we spend less time transmitting, more time waiting for propagation. So a general trade-off is that the larger the propagation delay is compared to the transmission delay, the less efficient we are. Of course, the header has an impact, the ACK has an impact, but in many cases they're quite small. And a general trade-off would be to compare the transmission and propagation delay. Of course, processing delay comes into it, but again, that's quite small. If we increase the propagation delay for the same transmission delay, the efficiency will go down. Or if we decrease the transmission delay for the same propagation delay, the efficiency will go down. So it's often about how the transmission delay of the data and the propagation delay compare to each other. Any questions on how we calculate the throughput and the efficiency in stop and wait? You need to be able to calculate them in exams with simple questions like we've gone through and more complex ones as well. And try and understand the trade-offs, that is, what will increase efficiency and what will decrease efficiency. You should be able to draw the diagrams, and like we went through yesterday, a simpler way to see what happens is to draw the diagram and see how long each step takes, and just add them up, and you get this total time. Transmission plus propagation plus processing plus ACK plus propagation gives us the total time. The efficiency, a way to express or calculate the efficiency, is given on this slide. How did we calculate over here? The throughput was what do we have? We had the payload divided by the total time for one exchange. And if we use the terminology here where data, header, ACK are transmission times, the ones we have over there, the transmission time of the payload plus the transmission time of the header plus the transmission time of the ACK, which is header plus ACK plus header plus data plus ACK plus 2 times the propagation. This equation omits processing time, just to keep things simple. You could include it if you wanted to. So in general, it's the data frame, which is header plus the data contents, ACK frame, the transmission time, and the propagation times. That gives us the total time, which is this part. And in the throughput, it's the number of bytes, the payload in bytes or bits, divided by that total time. That's what we did here, and we got our throughput. Well, the efficiency is very similar, except instead of having bytes here, it's a ratio between the time we spend transmitting those bytes and the total time. So instead of bytes here, the efficiency is, let's say in the same terminology as on the slide, data measured in our case seconds. That is the payload transmission time. And we get the 1 on the slide. efficiency, throughput, where the difference is this is the bytes divided by the total time. This is the time spent sending those bytes divided by the total time. And you get these values. You see that differ simply by the data rate. In our example, the data rate was 1 megabit per second, so we had a payload of 1,000 bytes. This value would be 1,000 bytes divided by 1 megabit per second, which is all we did here. We took this value and divided by 1 megabit per second and express it as a percentage. And we get our efficiency. And the general trade-offs, if we have a high data rate, a long link, a high propagation delay, or small data frames, the efficiency will go down. That is, high data rate, this value will go down because the time spent transmitting goes down. Large distance link, propagation delay goes up. Therefore, this value goes down. Small data, then the header relative to the data goes up, and therefore this value goes down. So they are some of the factors that impact upon the efficiency of our stop and wait protocol. So not good, for example, for satellite links, because a satellite is thousands of kilometres up away from the transmitter. Not so good for, say, optical links where our data rate is very high. So we need an alternative. In some cases, we need something that's better, more efficient. Before we look at the alternative, and I'll pass out some handouts. Any questions on stop and wait? So some of you have these, some may not. I've got more. Just take one of them. If you didn't get one yesterday, take one. I think you have it in your handouts, but it's just, this one's in colour and it's much easier to see. Any questions on stop and wait? Thanks.
From the data, why is in second?
In the formula on the screen, the data is a measure of transmission time. Time of the data on this, in this equation, on this slide, is that all these values are in time units. So data, header, ACK and prop are all measuring time, where data represents the time to transmit the payload. We called it payload here, but it's the time to transmit the real data. So if I've got 1,000 bytes of payload and my data rate is 1 megabit per second, the value of data would be 8,000 microseconds. The time to transmit the real data. That's the value of data in this equation. It's slightly different terminology that we used on the board. So it's the time to transmit the real data divided by the total time, which is really graphically the time to transmit the blue part here divided by the total time. That's our efficiency. The more time we're spending transmitting the real data, the more efficient we are. Any other questions?
What is payload?
Payload is the real data that we carry. I want to get data from my computer to computer B. That's the payload. We add headers, trailers, we send ACKs. They are not payload. They are not the real data. They are overheads. So the payload is the original data that we want to transfer from A to B.
So total payload is 3,000.
In the question, we had a total payload of 3,000 bytes, correct? But we split it into three data frames in the original question, yes. We often refer to the payload of a packet or a payload of a frame. A frame is this big, some part is header, some part is trailer. The payload is the real data that we carry in that. What's the problem? Well, we know it's inefficient. How can we make it more efficient? Without changing the link parameters, we cannot change them sometimes. The distance is fixed, the data rate is fixed. What's the problem with the protocol in terms of inefficiencies? What's the problem here? What causes the inefficiency from the protocol perspective? The ACK, what could you do differently? Well, we need an ACK. Well, what the ACK is used for in this case is for the receiver to tell the sender when it's allowed to send another frame.
It should be the buffer time.
Even if we have no time spent waiting here, it's still, if the propagation delay is large, it's still inefficient. What we'd like to do, and that's what the handout in front of you will show, in this case we can send one frame per, we can send one frame and then we have to wait for it to propagate and wait for the ACK to propagate back. That's inefficient when the propagation time is large because we have to wait a long time. So the idea of the next scheme, the sliding window scheme, is to allow the source to send multiple frames before it has to wait. Enough frames such that instead of, so we transmit the first and ideally transmit another such that we don't have to wait long before the ACK comes back. We don't spend, or ideally we spend no time not transmitting. We'd like to spend all the time transmitting instead of waiting. So allow the source to send multiple frames. Stop and wait allows the source to send one frame, then wait for an ACK to come back. Sliding window allows the source to send multiple frames. We'll come back to that one. Allows us to send multiple frames and then have to wait for an ACK to come back. So an alternative to stop and wait, called sliding window flow control. We'll see why it's called that shortly. Stop and wait allows us to send just one frame. So one frame can be in transit, we say. By in transit we mean it's propagating across the link and then the ACK is propagating back. With sliding window we want to allow multiple frames to be in transit. So if we think here's the link, there are multiple frames flowing across that link at the same time. And then there's ACKs coming back. We want to make use of the link. That is, we want to have data on the link as often as possible. Allow multiple frames to be in transit or to be transmitted before waiting for the ACK to come back. We'll see that it can be more efficient than stop and wait. But we'll also see it's more complex than stop and wait. Stop and wait, the one advantage, it's very simple. But in terms of implementing the transmitter and receiver, you just have to have those simple rules. Here it's more complex, and one thing we'll see, we need to keep track of the frames that we transmit and receive. Yeah? I don't know if I mentioned it. Right, I think I skipped over it, but I should have mentioned it yesterday. So far, with flow control, where was it? We're assuming no errors. So we're making the assumption that whenever we transmit a frame, it will arrive at the destination. Nothing will be lost. later when we look at error control, we'll see what's the impact of errors. So for now, no errors. Later we'll see what errors, how errors can be fixed. We're going to allow the source to send multiple frames before an ACK comes back. Stop and wait, we send one, wait for an ACK. Sliding window, send, let's say, 10 frames and then wait for an ACK. If we do that, we need to keep track of which frames we have sent. And we'll see why when we go through the example you have in front of you. So in fact, we keep track of frames by giving them numbers. Frame number 1, frame number 2, 3, 4, and so on. And sequence numbers. So in the header of each data frame, we include a sequence number, a number indicating this frame in the sequence of the data. And because the header is normally a fixed size, we only have a short amount of space to represent these numbers. So we have, say, a k-bit sequence number. And with a k-bit sequence number, we can represent values from 0 up to 2 to the k minus 1. Okay? If k is 2, that is, we have a 2-bit sequence number, means we can have 0, 1, 2, and 3. And if we have 10 frames to send with a 2-bit sequence number, the first frame would be 0, then 1, 2, 3. The fifth frame would be 0 again. We need to wrap it around. So it'll be 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, okay, for 10 frames. So with a k-bit sequence number, we go from 0 up to 2 to the k minus 1 and then wrap back to 0 and keep going. If we have an infinite amount of data, we just keep wrapping around. So we give each frame a number, a sequence number. And the source and also we'll see the receiver keep track of the frames which have been sent and have been acknowledged. Let's explain how that works. Let's make some space for our examples. Well, you'll see the example, and the coloured one in front of you is one we'll go through shortly. But the idea will be that the source can send multiple frames, and then eventually an ACK will come back, say for the first frame, and then it will start to transmit more frames. That's the idea with sliding window. With stop and wait, this is sliding window. Stop and wait, we send one frame and then have to wait for the ACK, and then send the next frame, wait for the ACK. With sliding window, we allow to send multiple frames, wait for the ACK, and then send multiple frames. More efficient because we're transmitting more often. That's the idea. For this to work, the source and the destination keep track of the frames that they've sent and the frames that have been acknowledged. In this case, this simple example, let's call this frame number 0, 1 and 2. This would be frame 3. At some point in time, easier example. At this point in time, from the source's perspective, it has transmitted frames 0, 1 and 2. It has not yet received an ACK back at this point in time. So it will keep some variable at the source. I have transmitted frames 0, 1 and 2. I have not received an ACK yet. And then a little bit later, here, it has transmitted 0, 1 and 2, and it has received an ACK for 0. And sometime later, it has transmitted 0, 1 and 2, received an ACK for 0, and also transmitted frame 3. So the source will keep track of the frames that it has transmitted already and the frames which have been acknowledged, with the idea that the frames, we're only allowed to have a certain number of frames outstanding. By outstanding, we mean we've sent them, but we haven't yet received an ACK. So, in this example, at this point in time, we have 3 frames outstanding. We've transmitted 3 frames. We haven't received an ACK for any of them. So we'd say we have 3 frames outstanding from the source's perspective. That is, we're still waiting for an acknowledgement. They haven't been confirmed yet. At this point in time, when we receive the first ACK, how many frames outstanding? When we receive the first ACK here, how many frames does the source have outstanding or that have not been acknowledged? How many? 2. Which frames? Frames 1 and 2. That is, transmitted 0, 1 and 2, receive an ACK for 0, therefore, in fact, 0 is complete. 0 has successfully been delivered and acknowledged, so in fact we can forget about that. From the source's perspective, there are 2 frames, frame numbers 1 and 2, which are outstanding. That is, they haven't yet been acknowledged. And when we transmit the next frame, then the frames outstanding are 1, 2 and 3. There are 3 frames outstanding. 3 frames we're waiting upon. With sliding window, we will limit the number of frames that we're allowed to have outstanding, and it will be related to the size of the buffer at the receiver. Remember, this is all back to flow control, making sure that we don't send too many frames to overflow the buffer at the receiver. If the receiver can accept 3 frames in its buffer, we should not send more than 3 frames, or we should not have more than 3 frames outstanding, because that could overflow the buffer if we send 4 frames. So the number of frames we have outstanding, that is transmitted but not yet ACKed, is important because that's going to be limited to ensure we don't overflow the buffer. What we'll do in these few slides is go through how we can keep track of the frames transmitted and ACKed, and then see the performance. That was just the concept. So, the source or the sender. In sliding window, the sender is allowed to send up to W frames. So W is some parameter for our protocol. It can be different values. It's allowed to send up to W frames without receiving an ACK. So if W was 10, if I send 5 frames, I'm allowed to send another 5 frames even without getting an ACK for the first frame. So I could send frame 1 through to 10, and after sending that 10th frame, I'm not allowed to send any more until I receive an acknowledgement. Okay? So the concept is that we have a limit as to how many frames we're allowed to send before we have to wait for an ACK. In stop and wait, what is W? In stop and wait, what is W? 1. In stop and wait, we're allowed to send 1 frame and then we have to wait for an ACK. Sliding window is an extension, or the other way, stop and wait is a specific instance of sliding window. Stop and wait, send 1 frame, wait for an ACK. Sliding window, you're allowed to send W frames and then you must wait for an ACK. So that's stop and wait is just the case of sliding window when W equals 1, a simple case. We can send W frames, then wait for an ACK. To keep track of this, the number of frames we've sent, the number of frames we're allowed to send, we can say that the sender records 3 variables. The sequence number of the last frame that was acknowledged, the sequence number of the last frame transmitted, and the current window size. And to illustrate how these values change over time, we'll use a diagram like this. What does it mean? Assume we have many data frames to send from A to B. So many data frames. In the example, we have in the example diagram, we have a 3-bit sequence number. In this diagram here. It's just an example, 3-bit sequence number. Why 3 bits, or why do I know it's 3 bits? Because we see it goes from 0 up to 7 and then wraps around 0 to 7 and keeps going, and assume it started back here. So at some point in time, this represents the frames transmitted and acknowledged. We'll explain why. But we have a 3-bit sequence number, meaning our sequence numbers go from 0 up to 7 and then wrap around. So the source has many data frames to send. Data frame 1, or the first data frame to be sent, would have a sequence number 0. The next frame to be sent, 1, 2. The 8th frame to be sent would have a sequence number 7. The 9th frame to be sent would have sequence number 0. And keep going. Okay, assume we have thousands of frames to send. We draw a diagram like this to represent the sequence numbers of those frames. And that's what this part represents. Some set of frames. Here we show, 14 frames. No, sorry, 16 frames. But assume there were some back here and there's further in the future. If we focus on these 16 frames, what the sender does is keeps track of the frames which have, or the last frame which was acknowledged. And in this diagram, at some point in time, it says, so this line here splits between the frames which have been acknowledged and those that have not. Last frame acknowledged is 5 in this example. The last frame act in the example is 5. Or the frame with sequence number 5. The last frame transmitted at some point in time in this example is 7. TX for transmit. Just in this example. And the window size, the current window size, in the example is 5. And it's shown graphically here as this sequence of frames where we keep track of, okay, this frame is the last one acknowledged, this one is the last one transmitted, and the window is this blue rectangle here showing that we can transmit another 5. The window, the current window, keeps track of the number of frames we're allowed to transmit at some point in time. It usually has a maximum value. For example, 7 in this case. We do not see that. We'll explain later. But if we have a maximum value, then the current window is those that we're allowed to send at this point in time. In our example, the maximum window size is 7. So in this example, and we'll see some more parts of it, the source is allowed to send 7 frames, and then it has to wait for an acknowledgement. So if I have many frames to send, I could send 7 and then I'd have to wait for some ACK to come back. One way we could draw that is using our time sequence diagram. Not so important to draw this one because we'll go through a detailed one on the coloured slide in a moment. But as a quick example, 7 frames, 0, 1, 2, 3, up to 6. The source transmits those, and if it's waiting for an ACK, maybe an ACK's going to come slightly later. If that's the first ACK comes back now, after transmitting the 7 frames, it cannot send another one until the ACK comes back. With stop and wait, we could transmit 1 frame and then wait and transmit the next. With sliding window, we can transmit W frames and then wait. In this example, the maximum window size, W, is 7, just in this example. So we could transmit 7 frames and then we may have to wait, and then we could transmit 4 more frames. What these 3 variables do is keep track of the frames we're allowed to transmit. In this example, it says frame 5 has been acknowledged. So in the past, I've transmitted these frames. They've already been transmitted, and we've received acknowledgements for them. So I've transmitted frame 0 and I received an ACK for that. So that frame has successfully been delivered. That's fine. Same with 1, 2, 3, 4 and 5. These are frames transmitted and also acknowledged. We can forget about them. There are 2 frames which have been transmitted but we haven't yet received an acknowledgement for. Frames 6 and 7. We've transmitted 6 and 7 but no ACK yet, according to this diagram. So they are somewhere in the network or in the link flowing towards the destination B, or the ACK is somewhere coming back. And in our example, we're allowed to send a maximum of 7 frames. We've got 2 outstanding frames. It means we're allowed to send at this point in time another 5. And that's the current window size. And that's the blue rectangle here. 2 frames are outstanding. We're allowed to have a total of 7 outstanding. Therefore, at this point in time, we could transmit another 5. If we transmit frame 0, then there'll be 3 outstanding, 6, 7 and 0. And we'd be allowed to transmit frames 1, 2, 3 and 4. So graphically, between this bar and the end of the blue rectangle is 7 frames. As we transmit frames, the blue rectangle reduces on the left because we can send or are allowed to send less because we've got more outstanding. And as we receive acknowledgements, if I receive an acknowledgement for frame 6, we can see that this vertical bar moves along. That is, frame 6 has now been acknowledged, and I'm allowed to send 1 more. Every time I receive an ACK, it means 1 frame's completed. It allows me to send 1 more frame. We'll go through the example to illustrate this again. The receiver does a similar thing. So the sender keeps track of the frames that have been acknowledged, transmitted, and the current window size. The receiver records the last frame acknowledged, received, and the current window size. So graphically we could represent it similar here, where from the receiver's perspective, it's received and acknowledged frames up to 5. It has received frames 6 and 7, but not yet sent an acknowledgement. Maybe they're in the buffer, waiting to be processed. It's only after they're processed do we send an acknowledgement for 6 and 7. And we expect to receive another 5 frames in the future. let's go through the example you have in front of you to show that. Where is it? So here's an example of sliding window. First, we'll go through the concepts and later we'll go through the calculations. So for now, we'll ignore the numbers. We'll just go through the concepts and then we'll come back to the numbers. So the color coding here is that this is some sequence of frames. Okay? Here we're using a 2-bit sequence number. We go 0, 1, 2, 3, 0, 1, 2, 3, and so on. And there may be more in the future. Okay? We just don't draw them. 2-bit sequence number, and the maximum window size is 3. Okay? W equals 3. So the maximum in our example is 3. Which means the source is allowed to send frames, 3 frames, before it has to wait for an ACK. And the color scheme is that green are the frames which, from the source's perspective, are allowed to be transmitted at this point in time. Red are frames which have been transmitted but we haven't yet received an ACK. And the grey ones will be frames which we've transmitted and we've received an ACK for. Think of those are frames which are complete, successful. So at the start, we've transmitted nothing. At time 0, nothing has been sent. So we're allowed to send frames 0, 1 and 2. Because for the maximum we're allowed to send is 3 here. We transmit in order, transmit frame 0 at the start. So once we transmit frame 0, from the source's perspective, we update our variables so that now frame 0 becomes one of those frames which has been transmitted but not yet ACKed. And we're still allowed to send another 2 frames because we're allowed to have 3 outstanding. We've got 1 transmitted, not yet ACKed. We could send another 2. If the source has data to send, it will send another 2. But if it has no data to send at this point in time, it may not, or it will not send. Okay? This means the frames which it's allowed to send. If it has no data, it will not send anything. In our example, it does have data. We assume it has always got data to send. So frame 0 is transmitted. We're allowed to send frames 1 and 2, so let's transmit frame 1. When we transmit frame 1, 0 and 1 are outstanding. We're allowed to send frame 2. The total here is 3. We transmit frame 2. So now frames 0, 1 and 2 have been transmitted but not yet ACKed. So we say they are outstanding. So now we must stop, okay? Because our limit W is 3. In this example, we're not allowed to send any more than 3 before we have to wait for an ACK. So we see transmit 1, 2, 3 frames and now wait for the first ACK to come back. We cannot do anything here. We're waiting. Stop and wait was transmit 1 and then wait. In this case, transmit 3 and then wait. So we're waiting, and eventually the ACK for the first frame comes back. Because of the propagation delay, frame 0 propagated, the small ACK was transmitted, and eventually arrives back. And when the ACK comes back, frame 0 has now been acknowledged. So we give that a grey box here because it's moved into the set of frames which have been transmitted and ACKed. Frames 1 and 2 are still outstanding, not yet received an ACK. Because 0 has been acknowledged, we're allowed to send 1 more. We're allowed to have 3 outstanding always. So frame 3 can be transmitted now. So we transmit after receiving the ACK. We say frame 3 is allowed to be transmitted, it's green. We transmit frame 3, so now 1, 2 and 3 are outstanding. This is the second ACK. This is the ACK for frame 1 coming back here. It arrives We receive the ACK for frame 1. Frame 1 becomes successfully completed. We're allowed to send one more frame 0. So we transmit frame 0, and now 2, 3 and 0 are outstanding. Frames 0 and 1, the first 2 frames, have been successfully ACKed. Slightly later, we receive the ACK for frame 2. Yeah. Frame 2 propagated, the ACK came back, 2 is complete. We're allowed to send frame 1. Frame 1 is transmitted, and now 3, 0 and 1 are outstanding. Do we have more? So we have 3 frames outstanding, frames 3, 0 and 1. The maximum we're allowed to have outstanding is 3, so we now have to wait for an ACK. So we're waiting for an ACK, receive an ACK for frame 3 here. So 3 is finished, allowed to send another one, transmit that other one, 0, 1 and 2 are outstanding, and we can keep going like that. Transmit frame 3, and I've stopped the diagram here, but we could keep going. So what do we see? First, we see our sliding window. The window is the number of frames we're allowed to have, or the set of frames we're allowed to have outstanding. We see the window is the green squares. Initially, it's 3 frames. As we transmit frames, the window closes on this side. It's 3. So the concept or the example is that we close the window on the left-hand side as we transmit frames. It gets smaller. As we transmit frames, the window gets smaller until it's fully closed. We cannot transmit any more frames. As we receive ACKs, the window opens on the right-hand side. When we receive an ACK, it opens. Transmit frame closes on one side, receiving ACKs opens the window, and over time you can see that the green boxes are sliding along in a set of sequence numbers. So we get what's called a sliding window flow control. And the slide that we had before about what does the transmitter keep track of, last frame ACKed, last frame transmitted, current window size, is just represented graphically here. That's all. In the implementation, there'll be just some variables that keep track. Okay, frame 0, last frame ACKed, frame 2, last frame transmitted, window size 1. And those variables will change over time. As we transmit frames, we are allowed to send less. As we receive ACKs, we're allowed to send more. And that changes so that up to a maximum allowed of 3 in this case. What else do we notice here? In this example, in this specific example, we send 3 frames, then wait for an ACK, send another 3 frames, wait for an ACK, and if we keep going, it would look like that. Transmit 3, wait for the first one to be ACKed, transmit another 3, ACK, another 3, ACK, and forever do that. In stop and wait, it was transmit 1, wait for an ACK, transmit another 1, wait for an ACK. This is more efficient because we can send more while waiting for that ACK. Any questions so far? It's more complex than stop and wait.
So for 2-bit sequence, that means the maximum is 3. So it's 2 to the 2 minus 1.
Yes. So also you've noticed that what's the maximum window size? Here we have a 2-bit sequence number, and I said the maximum window size, here uppercase W, is 3, which is 2 to the power of 2 minus 1. Why? Why not 4? Why don't I set the maximum window size to 4? Or 5 or 6? It's maybe not so obvious.
The frame numbers will repeat.
Yeah, if I had a maximum window size of 5, for example, then I'd be able to send frames 0, 1, 2, 3 and 0. Okay? Now, the acknowledgements, when they come back, contain a number indicating the frame that they're acknowledging. So when we send frame 0, in fact the ACK number that comes back says, thank you for that frame, I now expect the next sequence number, which is 1. So this is data frame 0, the ACK would have a number in it, 1 in fact in this case, saying the next expected. Now if we were allowed to send 0, 1, 2, 3 and 0, when we receive an ACK, which frame does it acknowledge? This 0 or this 0? We don't know. In general, it could, if things go out of order, and in practice things could arrive out of order, then we don't know if we transmitted frames 0, 1, 2, 3 and 0, and we receive an ACK saying, thank you, I just received frame 0, we don't know if they mean this frame 0 or this frame 0. Although we don't have errors in this case, we'll see later we can have potentially reordering of the frames, and we wouldn't know which one was acknowledged. That's why we limit this to 3 in this case, so that we don't get confused at the receiver as to what the acknowledgement is acknowledging. If I transmit 2 frames with the same sequence number 0, and I receive an acknowledgement saying, thank you for sending me frame 0, I don't know which of those 2 frames it really acknowledges. It could be one or the other. So we limit the number of sequence numbers we're allowed to send. So we never transmit such that we can get confused by the acknowledgements. And it turns out with a sequence maximum window size of 3, that's possible. It's the maximum window size. We could have a smaller value. It's okay to have a smaller value, but it's normally considered less efficient. Typically, if we have a 2-bit sequence number, we'd have a maximum window of 3. 3-bit sequence number, maximum window of 7. 4-bit sequence number, maximum window of 15, and so on. That's typical. Any other questions? In the same way as we did with stop and wait and calculate the throughput and the efficiency, we can do for sliding window as well. Before we do that, any questions about how the protocol works? You can transmit frames up to a maximum number outstanding, W in this case. So you can have no more than W frames outstanding, that is transmitted and not yet ACKed. And we keep track of those transmitted and ACKed so that the source knows how many it's allowed to send. And we use sequence numbers to keep track of them. This example also has numbers on it because I've created some simple scenario where we've got a propagation of 200. There's no units given in this to save space, but let's say 200 microseconds, it doesn't matter. 200 is the propagation delay. Data transmission is 100. So from here to here is 100, where 10 is the header and 90 is the data. So of that frame, 90% is real data, the rest is header. I just created the numbers so we can do some calculations. And the ACK transmission is 10. And you see in blue the numbers, if we follow through, 0 to 100, 200, 300 is transmitting the first 3 frames. The ACK for frame 0 will arrive at time 300. Start transmitting at 0, finish transmitting at 100, propagation of 200. Sorry, not the ACK, the data arrives at time 300. transmit the ACK back, the ACK will arrive at 510, which is really 100 plus 200 plus 10 plus 200. That's the ACK for the first frame. Similarly, you can calculate the ACK for the next frame and so on. ACK for the second frame at 610, ACK which allows us to send another frame, ACK for the third frame at 710, which allows us to send frame 1, and we can calculate the ACKs for those frames and so on. But we see it repeats, similar to stop and wait. Stop and wait, one data frame transmitted, stop and wait for the ACK. Here, we'll see if you keep going forever, 3 data frames transmitted, have to wait for the first ACK to come back. Then it turns out we can transmit 1, then another, and another 3 frames. The ACK will come back, and if you keep going, another 3 frames. ACK will come back, another 3 frames. So the performance. We're transmitting 3 data frames, in this example, every 510 units. The first 510, then another 510, and then another 510, and so on. So 3 frames every 510, let's say microseconds. Each data frame contains how much real data? How much real data? 90 or 90% of the entire frame. What's our efficiency? Or how do you calculate the efficiency? So a data frame, we spend 90, and I've added a time unit here, microseconds is the total time to transmit or to deliver 3 frames. Transmitting 1 frame, we're transmitting real data for 90 microseconds. So every 510 microseconds, we're transmitting real data for 3 times 90. 1 frame, we're transmitting real data for 90 microseconds, but we in fact transmit 3 frames. So 3 times 90, and the answer is on the slides, or on the 52.94%. This is a fraction, or you express it as a percentage. In that example, because I just gave the numbers, I didn't give the data rate. So we don't really know the throughput. We do know the efficiency though. If I knew the data rate was 10 megabits per second, if the data rate was 10 megabits per second, the throughput would be 5.294 megabits per second, 52% of it. If under the same conditions we use stop and wait, what would the efficiency be? Calculate the efficiency if we use stop and wait in that scenario. Anyone? If we use stop and wait in that scenario, what would the efficiency be? Stop and wait, we transmit 1 frame and then we wait for the ACK. In the sliding window, we transmitted 3 frames and waited for the ACK.
Up 3, right? Because you got here with us.
Stop and wait.
Have the total 10, right? Or just
1 million frames.
This number is 52% in terms of per frame, right?
No, the efficiency of using this protocol is we use 52.94% of the link in sending real data. It's in fact, in this case, independent of the number of total frames. What's the efficiency if we use stop and wait? If you drew stop and wait, you could follow this. It would be frame zeros transmitted. We wouldn't have 1 or 2 transmitted, okay? Because with stop and wait, we transmit 1, and then we stop and wait for the act to come back, okay? So if we drew it, you'd have to delete 1 and 2. The act would come back at 510 because it's the same values. Then we transmit frame 1, and the act would come back 510 time units later. And frame 2, 510 would be able to transmit the next frame. So with stop and wait, we transmit 1 frame every 510 time units. If I draw in a small, what we get in the sliding window looks like this. 1/3. This is what we drew with sliding window. With stop and wait, it's like this. You see, here we transmit 3 every time period, here just 1. Stop and wait is sliding window with the window equal to 1. So we transmit not 3 frames in 510, but 1 frame. What is it? 6. 1/3 of the sliding window. So the efficiency of using stop and wait in the same link as using this sliding window is 1/3. It's much worse in terms of performance. Still, 52.94 is not great. I pay 10,000 baht a month to use my link. I'm only using it half of the time. I should have paid for a better protocol or a cheaper link. How do I increase the efficiency? With sliding window. Increase the number of frames that I can send before waiting for an act, which will lead to increase in the sequence number. Note that what we have here is transmit 3 and I have to wait a little bit. Then the act comes back. Transmit 3, wait a little bit, act comes back. What I would like is this. Transmit. I'd like to be transmitting all the time. Act comes back. Acts, that is, I'm transmitting all the time up until the first act comes back. And even then the next act comes back, I can keep transmitting. That is, here we have a window, or we have stop and wait, which was really a window of 1. In our first example, we had a window of 3 with sliding window. Increasing the window increases the number of frames we're allowed to transmit before waiting for an act. 4 would be like this, 5, 10, and so on. Increasing the window can increase our efficiency. And you have the answer in front of you, the second case. Same scenario, but a 3-bit sequence number, a maximum window size of 7. I'm allowed to send frames 0 to 6 at the start. Transmit 0, 1, 2, 3. I'm allowed, after transmitting the first 4 frames, I'm still allowed to send another 3 frames because my maximum window is 7 in this case. I'm allowed to send more. And in this example, it turns out that, okay, this is 100, 200, 300, 400, 500. At time 510, down here, I received the first ACK. I've transmitted frame 0, 1, 2, 3, 4, and even started to transmit frame 5 at this point in time. So I'm here. I've transmitted frame 0 to 5, and then I receive an ACK for the first frame. So frame 0 is acknowledged. So it allows me to send one more. I'm still allowed to transmit 6, but because I've received one ACK, I'm now allowed to transmit frame 7. I transmit, note I can only transmit as fast as the data rate allows me to send. That is, I have to do one after another here. So I transmit frame 5, and then frame 6. Here, I transmit frame 6. But then I receive an ACK for the second frame, frame 1. That allows me to, so frame 1 becomes ACKed. That allows me to send one more frame, which is frame 0. So I'm allowed to send 7 and 0. I transmit frame 0. Transmit frame 7. So 7 is transmitted, 0 I'm allowed to send, but I just receive an ACK for the third frame, allowing me to send one more. And this will keep going forever. I'm always allowed to send at least one more frame, in some cases 2. And as long as I have data to send, we'll see that it keeps going where I'm always allowed to send at least one frame. That's ideal in terms of our efficiency because we're always transmitting. There's no time spent waiting. That's what we like. A larger maximum window size allows us to send more frames before waiting for an ACK. And if we have it large enough compared to the propagation delay, then we may never have to wait for an ACK, which is in this case. Performance, what's the efficiency? Again, you have it. We're always sending in this case. Always transmitting, always receiving. The only overhead is the header. Because we're always transmitting, no time waiting, the only wasted time is the time transmitting the header. So 90% of what we transmit is data, real data, 10% is header, so our efficiency is simply 90%. That's the best case we can achieve if we have a 10% header. The only way to increase this efficiency would be to change the header size to make it smaller. But assuming that's fixed, that's the best case we can achieve. So that was with W equal to 7. They're out of order, but the first one, W equal to 1, was stop and wait. We got 17% efficiency. The first sliding window, we had W equal to 3, and we got about 53% efficiency. With W equal to 7, we just got 90% efficiency. What about a 4-bit sequence number? 4 bits means W equal to 15. Efficiency, same as W equal to 7. Even with more bits, we will not get any better than here because we'll always be transmitting again. So increasing any the window size more doesn't improve. We've reached the maximum. It depends upon the propagation delay and the transmission time. In this example, W equal to 7 gives us the highest, and anything above 7 also gives us that maximum efficiency. If our propagation delay was different, then that may not be the case. What we want is a window size such that we're allowed to send frames so that within one exchange we're always transmitting. In this case it took 510 time units here. With a window size of 3, we didn't transmit all of the time. We only transmit for 300 out of the 510. If it was 4, we'd transmit for 400. And for 5, up to 510. Window size of 6 would be good enough because we'd be transmitting for all the 510 of waiting for the first act. So the optimal window size or the optimal maximum window size depends upon the time it takes to get that first act. Here it took 510, so our window size needed to be large enough to transmit data for all 510 time units. Anything larger and we'll reach the maximum efficiency. Let's continue next week. What you should do is, for the quiz this week, you've got 2 weeks to do it. That is, it's not due next lecture because in fact the quiz covers this and the next set of topics on error control. So you can try the quiz, but it's not due until almost two weeks' time, not next Wednesday, the Wednesday after. But try to understand the calculations used in stop and wait and sliding window flow control. Next week we'll go through error control, and it turns out error control uses these same techniques. Still uses stop and wait and concepts of sliding window. So it's important to understand these to understand error control. Enough for today.